This is video 7 in the forces topic. In this video, I'll go through different applications of Newton's laws. So Newton's laws give us the basic tools for solving a variety of problems, which at first glance don't really seem as though they could be solved using the same principles. And in this video, I'll go through the first 4 of those. So the general methodology that I will be following is the same as that I used in the motion topic, with a couple of small differences. So the diagrams that we will draw are free body diagrams. We will always resolve the forces, and we will always find the net force. So the first application that we'll look at is that of lifts or elevators. So in this question, we have a man standing in a lift, standing on a set of bathroom scales, and we're asked to find the reading on the scales. In 2 cases, in the case that the lift is stationary and in the case that it's accelerating downwards. So to solve our problem, step 1, we draw a diagram, we label our coordinate system, and we label all the forces acting. So we know that we have the weight force of the man on the scales, and we have the equal and opposite normal force of the scales on the man. We also know in this case, because the lift is stationary, we have no net force acting on the system. So the next question is, what is it that we want? So we want to know what the scales will read, and we need to figure out which force it is that will give us that. So I'll get you to pause the video and have a think which one you think it is. And the answer is, in this case, that we want the normal force. The reason being that the normal force is the contact force between the man and the scales. So the normal force gives us the equal and opposite force of the man on the scale. So by finding the normal force, then we have the force applied to the scales. The weight force will never change unless the acceleration due to gravity changes. This will become clearer when we answer the second part of the question. So our next step is to find our net force, or to find an expression for our net force. So we know that our net force is equal to the mass of our object of interest times the net acceleration on that object, which in this case is 0. The net force is also the sum of the individual forces in the system. So we sum up those, taking care to make sure we have the directions correct. In this case, I've made the normal force in the upwards direction positive, and so the downwards net weight force is a negative. Solving, we find that the normal force is equal to the weight force. That is, the scales just read the man's weight, which, since the scenario is exactly the same as the man standing on the ground, is what we expect. In part B, we're told that the lift is accelerating downwards with a constant acceleration. So, diagram and label the forces. Once again, we have our weight force down, our normal force up. And in this case, we know that we have a net force acting on the system in the downwards direction. We know again that we want the normal force, and so our next step is to find the net force in this case. So we know that our net force is equal to the mass times the net acceleration, and we know the net acceleration is down. So our net force is negative. We also know the net force is equal to the sum of the forces in the system. In this case, again, we have the same as previously, the normal force upwards and the weight force downwards. Solving for the normal force, we find that a normal force is equal to the weight minus the net force on the system. So in this case, the reading on our scales will be reading less than the man's weight when the lift is stationary. And since this is something that we can experience, we know that that's likely to be true, because you generally feel a lot lighter when the lift is accelerating downwards. I will present each type of problem as a separate video on this page, and give you a chance to practice in the middle.